So we just talked about starbursts, those spectacular things that happen of in centers of galaxies. Some of those galaxies that form stars at rates and efficiencies that are hundreds of times more higher than what we see in the center in our whole Milky Way, in the arms of the spiral arms of our own Milky Way. But there are some galaxies that display even more incredible phenomena, and those are extreme amount of radiation and sometimes powerful jets of material emanating from deep in their centers. They're definitely unusually bright, and besides being unusually bright, there are some other things we're going to talk about. But anyway, every time we meet one of those galaxies, and they only happen in about 10% of all galaxies. Those are called active galactic nuclei, the plural of the nucleus, active galactic nucleus, or AGN. Many astronomers refer to them as like AGN. I'm doing AGN physics, myself being one of those. All right, now the quasars, of which we have one image here, are some of the most luminous examples. The name quasar comes from the fact that they look like stars in the sky, and therefore they were first named quasi-stellar objects, or QSO, and then they became quasars. This is where the name is coming from. In case you wondered. Okay, and it's very, very interesting how they were first found. So I said they look like stars, right? So kind of like boring point sources in the sky. They look like stars, but then astronomers took spectra, right? So they spread the light coming from, so they put basically a prism or a slit, more likely. So they spread the light into its components, and they looked at the intensity as a function of wavelength, and they found some amazing things, some emission lines. And here's a quasar. Let's try again. Named 3C273 because it's just part of the catalog, is the 273rd object catalog. Anyway, and we have here some hydrogen emission lines, basically. And the weird thing is that they did not show up. So they showed up in their spectrum much longer wavelengths, right? So we have, see, the wavelength increases this way. So we have usually comparison sample, that is maybe some hydrogen emitting gas in the laboratory, okay? And here are the same H delta, H gamma, and H beta that are seen in that quasar, but they are seen, you see, shifted, right? Shifted towards longer wavelengths, all of them, and by the same amount. Shifted by the same amount. And it was actually that change, that shift in wavelength we calculated, and that was the sign that the object that emits these lines, actually, these objects is very far away. Okay, highly redshifted spectra indicate large redshift, cosmological redshift, or large distances. Okay, so now we have the brightness, or what we measure, the intensity of the light that we measure in at the surface of the Earth, that is with our telescopes, and then we have the distance. Of course, we can find the luminosities, and we found out that for many of these distant quasars, we can calculate luminosities. So luminosity of a quasar is 10 to the 12 solar luminosity. So basically trillions of times more luminous than the sun. And then the very interesting situation comes from measurements of the variability. So we have brightness or intensity as a function of time, and it shows variability. And then we measure, some periodicity, right? And what do we get from this? We basically put some limits on the size of the region that emits this light. It's basically, if we find, for example, that this is 50 hours, that means that kind of box or region of space cannot be larger than 50 light hours, for example, and you can convert that in light years if you want, right? So it's basically, if you think, okay, if light is the fastest thing that travels out there, right? Light must be able to travel this distance in 50 hours or less, right? So basically, the size of the region that emits that light cannot be, right? So it's smaller than 50 light hours. And we found out that for these quasars, those regions are smaller than our own solar system. So imagine we have this a region, something in this universe that is as big as one solar system. However, it's like it packed inside a trillion of suns. So what happens there? It turns out that what happens there is a supermassive black hole around which there is gas that swirls very fast, and because of the viscosity, the material, the friction in between the atoms and the charges in that material that swirls around, heats up at tremendously high temperatures and emits that light that we see as quasar. All right, so quasars are basically light emitted by material swirling onto supermassive black holes. We were just not able to find any better explanation for that. What do we mean by supermassive? 10 to the 6 to 10 to the 9 solar masses. So that's basically millions to billions of solar masses. We have evidence for the existence of supermassive black holes. Supermassive black holes, and this is one of them. This is a different kind of observations. Some other observations are obtained from a more nearby AGN. So maybe not necessarily a quasar, but things that happen in centers of galaxies that are actively emitting huge amounts of radiation. So here we measure the intensity and speed of gas around that very nucleus, right? So we see basically, because we measure the wavelength of the emission, we see that this blob of gas is moving kind of towards us, right? If we are, kind of somewhere here, so we observe, this would be the line of sight. Okay, so we see that blob of gas moving towards us, and therefore is going to be blue shifted, right? So the light that's coming from that blob of gas is blue shifted, and then the other one, we see it as moving away from us, and we deduce that because that light is redshifted, the spectrum that we obtain from that part of the gas, and from the blue shift and the red shift. Okay, it's the orbital speed basically. We measure, right? So we have the orbital or rotational speed. Okay, and we can tell with the radius, right? And remember, we actually talked about that formula. So we have the radius, and then we divide by that universal constant of gravity, and we calculate the mass of that central object that keeps gas orbiting. And it turns out that central object, which is also kind of dark, we don't see it, that turns out to be 2 to 3 times 10 to the 9, the billion, times the mass of the sun, right? So what would you call that? That is a supermassive black hole. That is basically the best explanation we have for this kind of fast rotation, right? So this, is the shift, the Doppler shift, in wavelength, and that through that we measure the rotational velocity. And once we have that, and obviously the location of the gas that for which we measure the Doppler shift, then we can calculate the masses of the thing that keeps the gas rotating. And it's amazing to find these huge numbers, right? So we have billions of times the mass of the sun. And here is another example of gas. Now it's molecular gas here. Moving, orbiting something. And here are basically observations. So we have orbital velocity as a function of distance from the center, or basically a radius here. Okay, so these are data points. And then we have, this is basically a mathematical model. And the match between the data points and the mathematical model, so the match gives that mass of the black hole, or the mass of the dark object in the very center, to be about 36 million suns. So this is 36 times 10 to the 6 solar masses. Okay, so very, very interesting. And these are just two examples. They're pretty clear. I mean, you don't find feeds of data with to a model that good that often, and that is irrevocable evidence for the fact. I mean, there's no other explanation as to what keeps that gas moving towards us, and therefore blue shifted here and red shifted, moving away from us. That can explain these kind of situations. That's an excellent match between the empirical measurements and the model. So we talked about the part B of these images. Now we have so that's for the same galaxy, which is called Messier 106 or M106. So here in the image we have a beautiful, a really new image, a composite image. So we have here visible light in yellow, and we have X-rays in blue. So these are X-rays, and radio waves in purple, which is kind of blended with the X-rays here, and the long wavelengths in infrared light, they are in red, and they reveal, so this is infrared, reveals star forming regions in the spiral arms of these galaxies. So we have X-rays and radio. Here I don't have the purple color, I would have used it here. This basically reveals the existence of another pair of spiral arms. If you look at it, they're kind of like, look at that, whoa, amazing, right? And there are some mini jets here that are spewed away. So we see the one that is above the disk, jets that are hitting the gas above and below the galaxy's disk. So amazing evidence for the existence of supermassive black holes in the universe. you're thinking, okay, well, the black hole is black, so um, people are calling that energy coming from a black hole. Well, it's actually not really from a black hole, it's from matter falling onto a black hole, and it's actually a super massive black hole. Okay, so basically the event horizon or the shorter radius of these kind of supermassive black holes are basically the size of the solar system. So what's happening here? You have gravitational potential energy of matter falling onto the black hole. That's going to turn into kinetic energy, right? Because the potential energy is lost as you get closer and closer to the black hole, but that becomes kinetic energy. So matter rotates or swirls around just before it falls onto the supermassive black hole faster and faster speeds, and actually it's very close to speed of light, 3 times 10 to the 8 meters per second, and that's the fastest you can get. And because there is friction and the matter as it falls onto that black hole, okay, it's black hole and it's kind of like the accretion disk, can imagine something like this, because as it falls, thanks to the conservation of angular momentum, there is going to be that matter is going to take the shape of a disk, and that disk is called the accretion disk, and there is friction between the atoms and molecules, and friction means thermal energy, and this is how hot photons in UV and X-ray photons are going to be emitted. And that's what we see. How are those actually created? About 10 to 40% of the mass energy, E energy equals mc squared, actually is converted into radiation. So this is what happens with very close to the black hole. So this is how a black hole powers the centers of quasars or some other active galactic nuclei. Are there black holes in how many galaxies? It turns out that actually many nearby galaxies show evidence for that swirling motion of gas or stars or molecular clouds around something, just like we have seen it happens in the very center of our own Milky Way. And so we believe that perhaps all of them, even those we didn't find evidence for, but especially the massive galaxies, they have supermassive black holes in their centers. And why do we believe so? So we put together measurements of masses of the black holes, and we compared those. So we have mass of the black hole, okay, and that's measured in solar masses here, and we compared that with the masses, like the how much matter is in the stars in the central bulges of the host galaxies of the black holes, of course, supermassive black holes. All right, and here's what we found. We found that the galaxies with smaller bulges have smaller black holes, and the galaxies with larger bulges have large black holes. They kind of go hand in hand. So basically, black hole masses correlate with sizes of spheroidal components of their galaxies. Interesting. Okay. And this is mainly for black holes, supermassive black holes that are not actually very active, especially in the nearby galaxies, in the nearby universe. Remember, we see the quasars, the most intense, the most powerful active galactic nuclei. We see them at really large redshifts. But this is for nearby galaxies. So we do see the black holes, they're just not as active. They don't produce jets or radioactivity around them. These are, they do have influence on things around them. So there is still gas and stars that are swirling around, but they're far from being as luminous. Those things that swirl around, they're far from being as luminous as the quasars. So that's why we call them dormant. Okay, and so that's why we believe that, because we see the quasars at large distances, that means we see them in the past, and basically what we see now in the backyard, in the nearby galaxies, are actually the relics of those quasars. And so the quasar-like stage was just a phase in the evolution of these galaxies that happened earlier in time. But this correlation is actually very interesting and important, as that kind of shows us that the development of the central black hole must have been related to the galaxy evolution, kind of like the monster in the middle, which is the center of the galaxy, knows about its host galaxy. And that is interesting in itself, because remember when we talked about black holes, we said, well, the black holes have influence only on things that are really close to the event horizon, okay? But the bulge, right, this is large and far away from the social radius of the black hole. So there is not expected actually to be much influence between the black hole, or correlation between the black hole itself and the things that happen at much larger scales, like in the bulge. And yet there is a strong correlation. And that's why we believe that the development, like putting together that black hole in the center, has something to do, it's related to however the host galaxy evolves. So, one of the greatest questions in astronomy nowadays is like, which one was first? Was it maybe the black hole that attracted matter around it, and maybe that's how galaxies were probably put together? Or was first galaxy, that big proto-galactic cloud that formed stars? Maybe some of those very first stars were massive enough to end up, after the supernova explosion, end up in massive, if not supermassive, black holes. So it's kind of like chicken and the egg problem here. We don't know which one was first, but we do have increasing evidence for the fact that they actually form and evolve together, those black holes in the galaxies. And actually, kind of related evidence for the fact that maybe the supermassive black holes regulate whatever happens or during the formation, the development of a galaxy. We do have, for example, things like these radio galaxies that contain, so here somewhere would be the AGN, or the accreting supermassive black hole in the center of that galaxy. But besides that, in these radio galaxies, we see vast jets of plasma. They're extremely correlated, and so these are the jets, and they travel, so matter travels fast, close to speed of light, and those are strong radio emitters. And the best explanation for that kind of radiation, so right, this is basically a radio image, and that radio electromagnetic radiation comes from charges that are accelerated by magnetic fields. In case you wondered. All right. Now we have these jets. They interact with the intergalactic material and form these lobes. Okay, so these are the result. Interaction of jets with the intergalactic material. And it's already intergalactic, like in between galaxies, because they are huge, they're very powerful, right? So they have a lot of kinetic energy, they go way beyond the galaxy itself, over hundreds of thousands of light years, right? So you see, this is basically the size of the galaxy. So compare that with, if you compare that with what we have here, we have hundreds of thousands of light years. Huge scales. And so we do believe that this kind of activity has actually the power of saying something about what's happening with the host galaxies themselves. So basically, sometimes they might deplete the galaxy of gas because it pushes everything away, and so there are no more. There's not a good reservoir of gas left to further form stars, for example. So anyway, as I have mentioned before, these are questions that are kind of in the works. We're actively trying to find answers and better explanations to observations, like interesting observations like this, trying to find out when in the life of a galaxy was that quasar phase, or active galactic nucleus, or AGN phase, and when and how is that related to the starburst activity, or how does that relate to other types of galaxies, which we believe are actually different phases in the evolution of galaxies, and we try to understand whether or answer questions as to whether all of the galaxies go through similar phases or not, and which go through which phases, and so on.